Welcome to the RETScreen 13 course, Hands-on Assignment 1 on Residential Scale Grid-Connected Solar Photovoltaics. In this tutorial, we will build a RETScreen case study based on a solar PV study for a college in California. The initial study has been provided in the course, but the data has been updated to the context of 2012 and adapted for a residential system size of approximately 17 kilowatts located in Ojai, California. The PV system will be installed on a carport presumed to be located in a college campus setting and that can also be used to recharge electric vehicles. To begin, let's open RETScreen 4 and fill out the Start worksheet. In the Prepared By cell, type your own name. For this type of project and any project related to electricity production, we will select Power as the project type and PV as the technology type, since it is the technology commonly used in residential or commercial scale projects. Of the 5 grid type options, we will select a central grid and internal load option, since our project will be a grid-connected project and will be feeding at least a portion of its electricity directly to the load. In order to use the more advanced cost and financial analysis functions of RETScreen, we should select a Method 2 analysis type. We will also select higher heating value because the project is located in North America. In order to pick the most appropriate location, let's look at a map of the campus at Thatcher School. Referring to the Google Earth map shown here, we can see that the project site is located in Ojai, California, at a latitude of 34.46 degrees north and a longitude of negative 119.18 degrees east. Let's look at a map from the RETScreen Plus, which is a performance monitoring tool that offers maps not available in RETScreen 4. As we can see, Ojai has been added to the map, and the Oxnard Airport and Camarillo are the closest options. Let's select the RETScreen climate data location. After selecting the United States as the country, we are offered a number of climate data locations. We then select California as the state and Camarillo as our weather station to get the annual and monthly climate data shown here. We get the following data. The general area around the project site is around 12,000 square kilometers and features mountainous and desert-like conditions. Compared to coastal areas in Southern California, inland areas tend to offer an increase in elevation, solar radiation, wind and temperature levels, and a decrease in relative humidity. The effects of higher temperatures on PV system performance should be easily offset by high winds, resulting in an expected increased performance of at least 1%. Another key difference between coastal and inland sites is that coastal areas typically receive a great deal of morning fog, which reduces solar radiation levels. As a result, inland sites might receive an additional 9% more radiation than those in coastal areas. Hence, we can expect around an overall 10% increase in the number of kilowatt hours produced by an inland system compared to a system on the coast. For a more specific site selection, we still will assume that the PV system will be installed in close proximity to the campus buildings in one of the parking lots. This presents a unique opportunity to utilize existing developed space and may allow the arrays to provide shelter for vehicles in the parking lot. Let's now consider the solar carport application we will be using for this project. Solar carports are a unique application for solar PV projects that offer multiple benefits, including utilization of pre-developed space, easy provision of additional capacity to projects that are constrained for space, shelter from weather elements such as heat and rain, and increased comfort to occupants who do not use air conditioning. Similar to buildings, they maintain their value over longer periods of time and appreciate as property values increase. Solar carports also provide easier access to PV panels for any required cleaning or maintenance than roof installations, and can be placed in unshaded areas. From an installation perspective, pre-assembled kits can be delivered and mounted faster than virtually any roof structures and cables can be pre-wired on the structural elements of the frame, reducing the cost of on-site electrical work. When considered for lighting purposes, a base case credit could also be attributed to relevant projects. Finally, solar carports can easily be converted into electric car recharging stations and provide an additional source of income through sales of electricity to vehicle owners. Today, there are many solar manufacturers of carports and a growing number of carports specifically designed for solar. Let's consider a specific technology from a reputable manufacturer, a California-based company that offers prefabricated carports. Let's assume 3 Orion carport units will be installed for a total capacity of around 15 kilowatts. We will now proceed to the load and network analysis. A small residential application in California will typically have monthly loads between 300 to 600 kilowatt hours per month, with a corresponding gross average load of 1 to 3 kilowatts. The chart shown here, taken from a study on the impact of distributed energy efficiency with solar on-peak load, gives us a better idea of the average residential demand peaks in California. Based on these charts, we will assume gross average loads as shown here, and enter these into the corresponding cells. The system peak electricity load over max monthly average cell is used to enter the system peak electricity load over max monthly average load for the base case power system. This represents the percentage that the peak electricity load exceeds the maximum monthly average power load over the 12-month period. For this, let's input a value of 80%, which corresponds to 2.5 kilowatts over an annual peak load of 4.5 kilowatts, which is expected for this project. The electricity rate base case cell is used to enter the average electricity rate for the base case power system. In recent years, California electricity prices have been estimated in the range of 13 to 15 cents per kilowatt hour for major utilities around the state. For 2013, let's use an estimate of 14.5 cents per kilowatt hour, adjusted with an 8% increase, which has been announced for the period considered as the project start. This gives us a rate of 15.7 cents per kilowatt hour, which we will put into the electricity rate base case cell. At this point, RETScreen generates a load graph to display the energy demand patterns. Here we also have the option to enter in a value for energy efficiency measures for the proposed case scenario. By implementing such measures, the proposed case graph on the right would change accordingly. As energy conservation and efficiency measures can be implemented at minimal cost for maximum results and would reduce the load and allow more electricity exports to the grid, we will assume that energy efficiency measures would be implemented for this project. Examples of energy efficiency measures that could be implemented might include lighting, appliance upgrades, efficient windows, passive solar design, and efficient cooling system upgrades. Altogether, these can be expected to result in a 30% decrease in energy use. Our completed load and network sheet should now resemble the one shown here. Let's move on to the energy model. Because this is a detailed residential scale project analysis, for analysis type, we will use the Method 2 option for the energy model. Let's consider the solar resource assessment. While California generally offers a fair amount of direct solar radiation, climatic factors will likely influence the energy output. Such influences might come from local fog, dust, dirt, cloud cover, humidity, wind speed, and other microclimatic factors at the specific project site. While it is good to be aware of such influences, calculating the effects of these is quite complex and is outside the scope of this analysis. For this project, we will utilize the solar radiation data from RETScreen. Referring to the solar radiation map shown here, we see that at around 6 to 6.5 kilowatt hours per meter squared per day, the solar energy source near the project site is attractive for a residential PV system. This is about 25% higher than the 4.97 kilowatt hours per meter squared per day provided by RETScreen for the Santa Barbara weather station, but we will go with the RETScreen data, keeping in mind that this is a more pessimistic value. Next, we will select the type of sun tracking device used to mount the solar collector. The options from the drop-down list are fixed, 1-axis, 2-axis, and azimuth. If the solar collector is mounted on a fixed structure, we might select fixed. The remaining choices may be selected if the solar collector is mounted on a tracker. A tracker is a device that supports the solar collector and moves it in a prescribed way to minimize the angle of incidence of beam radiation on the collector's surface, thus maximizing incident beam radiation. Available solar tracker options include 1-axis trackers, which track the sun by rotating around an axis located in the plane of the collector, azimuth trackers, which have a fixed slope and rotate about a vertical axis, and 2-axis trackers, which continuously position their surface normal to the beams of the sun by rotating about 2 axes. For this case study, we will begin by selecting a fixed axis tracking scenario. Later, we will explore a dual axis tracker option to assess the potential for greater energy production. For the slope, we will enter the angle between the solar collector or the tracking axis and the horizontal in degrees. Depending upon the goal of the system, it may be oriented for maximum yearly production, summer use, winter use, reduced capital cost, or for integration into the building architecture. Because this is a unique residential project aiming to generate the most energy and revenues possible year-round, for a fixed system, we will select a slope that is equal to the absolute value of the latitude at the project site. Several RETScreen simulations indicate that 30 degrees will result in a higher energy production. This is also close to our latitude value, so we will use it as our slope. The azimuth cell is used to enter the angle between the projection on a horizontal plane of the normal to the surface and the local meridian, with 0 due south. The preferred orientation should be facing the equator, in which case the azimuth angle is 0 degrees in the northern hemisphere and 108 degrees in the southern hemisphere. Note that the azimuth must be entered with respect to truth south and not magnetic south. Compasses point to magnetic south, and azimuth directions based on this measure must be adjusted for the magnetic declination. Looking at the magnetic declination